second session. So we are happy to have a Professor Run-qiu at Tianjin University in China. And he's going to talk about upper bound about cross sections inside the black holes. Thank you.
Okay. I first thank Professor Kim to invite me to give a talk here, and I'm very happy to have this chance to share my recent work. So my talk is about upper bound about cross sections inside black hole. So in my talk, I will talk about 5 points. Firstly, I will give some background and motivation. Then I will give some detailed examples about the bound of cross-section in iron black hole, BTC black hole. And then I will explain why this bound has the relationship to the condensate growth rate in holographic condensate. And in the first point, I will give a very short explanation about how to prove this bond in some situations. And then I will give some discussion and summary. Okay, we know the black hole is a very dense
excuse me, Run-qiu.
Okay.
Yeah, somehow yeah, now it's much better. It's about the mic.
Maybe I don't know. So there's something wrong.
No, now I can hear you clearly, but I mean, 10 minutes ago, 10 seconds ago.
Maybe I should adjust my micro.
Okay,
can you hear me now?
Okay. Yeah, now it's okay. Yeah.
Okay. So we know the black hole is a very dense object in the universe and have many beautiful physical and mathematical properties. And in many situations, such property can be presented by some universal inequalities. For example, we have a positive mass theorem. It is inequality. And we have the second law about the black holes. It shows the area of the horizon cannot be decreased in some physical processes. And we also have very famous inequality. It is the Ponner's inequality. It tells us the lower bound of the mass for a black hole. So currently, almost all such inequality only involve the horizon and is outside. However, recent studies in holography show that the inner range also have some boundary correspondence. For example, the condensate growth rate, we have found that it is connected to the inner range of the black hole. So it's near any universal inequality inside the black hole rather than the outside or horizon. So this is my main question. In order to answer this question, so I try to study a very simple object and try to understand if this object has some universal inequality. So the simplest object is the volume of interior. If you consider a D+1 dimensional black hole, for example, the Schwarzschild black hole, and you can compute the inner volume. However, when you really make some computation, you will find this volume is infinite, because simply you can find the mathematical expression for the volume inside the black hole. It's just this integration. And if you really make integration, you will find it is infinite, because all this quantity is a constant, but you have to make an integration with respect to time t. But t can go from negative infinite to positive infinite. So this integration will be infinite. However, you will find this infinite is very trivial infinite just because time t is a Killing vector. So I can just define a cross section. I do not make the integration with respect to t. I just care about the cross section. And you will find this cross section just this side, this guy. It's finite. And after some simple algebraic computation, you will find in Schwarzschild black hole, this cross section has a upper bound. This upper bound is proportional to the mass of the black hole. So we at least for the Schwarzschild black hole, I have found a universal inequality, or maybe not as universal, just for the Schwarzschild black hole. So my question is, if I want to understand if this inequality is universal or just correct for Schwarzschild black hole. So I want to study some more general black hole and to check this inequality. Before we do that, we have to give a very exact definition about what is the mean of the size of cross-section. In Schwarzschild black hole, we can just write down the mathematical expression, but in general black hole, we have to give it an abstract definition. So I define the size of cross-section in this way. So you can, for your first thing, you can choose an arbitrary co-dimensional 2 space-like surface inside the black hole. For example, here as d-1. And because we think about, we consider the stationary or static black hole. So we have a K-ning vector Kc, and this K-ning vector gives us the coordinate time t. So we have the K-ning vector Kc, and then we can choose a normal vector n. This normal vector, it is normal to Kc and also normal to the the cross section as d-1. So I just show it in this figure. I lose my mouse. Okay, so just to show in this figure, we have a cross section, the d-1. We have K-ning vector Kc, and then we choose a normal vector. It is normal to Kc and also normal to as d-1. Such normal vector n, in fact, it is uniquely up to an orientation. So in this sense, the size of a cross section divided in this way is unique. And we also only consider the maximal extended cross section because we want to know its upper bound. So we only consider the maximal extended cross section. Okay, this is a mathematical definition. And here I give a geometrical picture about what is the mean of the size. Firstly, you have cross section and you have a normal vector. Then you can always choose a co-dimensional 1 surface. And so that n is the normal vector of MD and S lie in MD. And then you will find the size of the cross section is just defined by the flux of the vector Kc along the cross section as d-1, because you will find the direct surface element is this guy, and then you will find this definition will become this mathematical expression. So from this mathematical expression, you will find the size stands for the flux of the vector Kc on the surface as d-1. So this is its geometrical picture. Okay, for a given black hole, we can choose many different co-dimensional 1 surface, and for a particular co-dimensional 1 surface, we can choose many different cross sections. So my conjecture is that no matter how you choose the co-dimensional 1 surface, and no matter how you choose the co-dimensional 2 cross section, and the size of the cross section always satisfies this inequality. If this Einstein equation is satisfied, the dominant energy condition is satisfied, and the boundary is asymptotic spherical planar ADS space-time. So this is my conjecture. Okay. In order to from my following talk, I will give a detailed mathematical expression about the size of cross section in a coordinate gauge. So I choose the coordinate gauge in this way. Locally, for arbitrary stationary space-time, I can always choose the coordinate gauge in this way. Because Vi is not 0, so this the black hole may have some angular momentum. And for arbitrary cross-section, we can always parameterize it in this way. So T equals T as xi and Z equals Z as xy. And after some algebras, we can find finally the size can be expressed in this way. So now I will give some example about this bond. The first example I consider the Schwarzschild black hole. So in general, it's the metric, the only metric component we will compute is just the F component. And the mass can be written in this way. So we can use this formula to compute the size, and we can find the max size can be read in this way. So this is, we just need to compute the maximum value for this expression. And after some computations, we can find this equation. So the maximum value and minus this guy will be in this guy. So if the topology is spherical or planar, then we can find the maximal cross-section will satisfy this inequality. This side is just the mass of the black hole. So we find for planar black hole or spherical black hole, my bond is satisfied in Schwarzschild black hole. However, if you consider the hyperbolic black hole, the k is -1, you will find here this is minus, and here we also have the minus sign. So the sign of this quantity is undefined. So in this sense, for hyperbolic black hole, we cannot ensure this inequality. In fact, if you give me a hyperbolic black hole, I can find some negative mass for this hyperbolic black hole, but the cross-section is always positive. So in this sense, for hyperbolic Schwarzschild black hole, this inequality is not true. But for spherical and planar black hole, this inequality is also true. So this is the result for a Schwarzschild black hole. So we can also consider the Rn black hole. Okay.
Yeah. May I have a question?
Okay.
Okay. Yes. So I'm lost in understanding the dimension of your cross-section.
Dimension, cross-section. Okay.
What is
in general, it has the dimension is almost the same to here. I missed something. It has the ADS radius. I'm sorry, here there's a typo. But the general, so the dimension of cross-section has the same dimension to the energy, the mass times the ADS radius. This is its dimension. The definition you can understand it by this simple expression. So it is just this guy.
I see. So so this cross-section is a codimension 2 object?
Yeah, it's codimensional 2, but it's not the area of codimensional 2 surface. Because you will find here, by this definition here, I make some projection. You understand it is, you may think it is some kind of projection of flux, not the area. So its dimension is not it's different from the dimension of area.
I see. And also you here discuss the maximum of this value. And
yeah, the upper bound, right?
Case of black hole background. So what is the shape of the cross section which gives you the maximum?
Sorry, can you explain a little more? I missed your
this cross section, and you seek for the maximum, right?
Right.
And what is the shape of this cross section when it is maximized?
In simple case, for example, in planar or spherical ADS black hole, its shape is just, for example, if you think about spherical Schwarzschild black hole, it is also a sphere.
I see.
In planar symmetry, it is a plane. But if you think about more connected black hole, I don't know what's the shape.
So it's inside of the black hole, but you measure the volume of this sphere and then you think of it.
Right, because even inside black hole, it is still a space-like surface. So we can define something such as volume. But here, the cross-section, the size is not the volume of surface, because I make a projection. So make a projection along the Canyon vector. If the Canyon vector is just orthogonal to this surface, then this guy is just proportional to the area. But in general, it has some relationship to the area, but it's not same as the area.
Nice.
So I call it is the size, not call it just the area or volume. So in some sense, it give us some how big of this codimensional two surface, but it's not different from the area.
And also, will you discuss some possible relation to complexity later? Is that it?
Yeah, I will show later. This guy has just gave us the complexity growth rate.
Oh, I see. That's great. So yeah.
Okay.
Thank you.
Okay, I will go on. Now, if we think about the iron black hole, the computation will be compacted. The basic idea is that because we want to find the maximal value of this guy, so I just use some mix the computer's derivative and find his set point, and use some mathematical technical. I can prove the maximum value will be decreased if I increase the charge. This guy, the current P is the maximal volume of this guy P. So I can find if you increase the charge P, this guy will decrease. So in this sense, the charge case, the maximal size of the charge case will always smaller than the neutral case. Because in neutral case, we have proved our bond is satisfied. So in charge case, we also have this bond. Also, I'm sorry here, I missed ADS radius. Okay, in about two examples, we think about a static case. Now I think about a stationary case. For example, the simplest stationary black hole is BTC black hole. So after a computation, I can find the maximal cross-section can have this expression. So you will find, because here it's minus the J square. If J is 0, this part gives us the mass, but here minus J square, and it shows this guy is smaller than the mass times ADS radius. So for BTC black hole, this bond is still true. So at current, I have shown some three simplest example, and in this three example, this bond is always it's true. This bond is true. So this gives us some so based on this example, so we guess this inequality may be true for very general class of black holes. So now I will talk about another thing. I will show this the size of the cross section. Although it is a pure geometrical quantity, it has a very strong relationship to the holographic complexity growth rate. Here I give a very basic introduction about what is complexity. So complexity is a conception coming from the quantum computation. And in general, we can use a circuit complexity to understand what is complexity. So if you have a reference state and you want to obtain a target state, and you have to prepare some quantum circuit so that it can transform one state into another guy. And you have made many different quantum circuits to realize this purpose. So different quantum circuits have different gates, and we can pick out the minimal gates. You can pick up this quantum circuit which have minimal gates, and this minimal gates number stands for the complexity between these two states. Okay, so in holography, and we can consider the thermal field double state in a static or stationary black hole. So in this black hole, the two boundary slices can give us a quantum state in the Sommerfeld double state. And then there are two holographic conjectures to compute the complexity of Sommerfeld double state in holography. The first one is the complexity volume conjecture. It says the maximum volume connecting two boundary slices give us the complexity of corresponding boundary state. And in this conjecture, we have the freedom to choose a length scale. So here I just choose length scale in this way. But in some cases, this is not a unique truth, but you choose different length scale in fact give us the same physics because it just depend on how you choose the union of the complexity. So here I just choose the length scale in this way. Another conjecture say the complexity is proportional to the on-shell action in a very special space-time range. This special space-time range is the Wiener divide patch. Here I just show in this blue range. At the beginning, the people after complexity action conjecture was proposed, people think this guy is better, CA conjecture is better because in some cases, people find this inequality. And this inequality is very famous in quantum computation because it tell us the maximal computation of the computer. So once this conjecture was proposed, the Susskind and the other guy found this inequality, and they say CA conjecture is better than volume conjecture. However, after then, more detailed computation show a different result. In many cases, we will find in volume conjecture the complexity growth rate will satisfy this curve. So we will find it is always bound by the mass. But in action conjecture, we find in some cases we can obtain this curve. So at some median time, the complexity growth rate can violate the Lenoid bound. So if you think the Lenoid bound is very important in quantity about complexity, in fact, the Lenoid bound in some sense rule out the action conjecture. Of course, you may think the Lenoid bound is not so universal. In holographic system, the Lenoid bound is not true. In this sense, we still believe the action conjecture. So there's a question. For volume conjecture, can we find some example to violate the Lenoid bound? In order to study this question, I want to study the volume growth rate in CV conjecture. So I find in volume conjecture, the complexity growth rate is just given by the size of cross section. To understand this point, here I firstly parameterize the cross section, the volume, the d-dimensional hypersurface in this way. So S is a parameter and xi is just a spatial coordinate. And then you will find the complexity growth rate can be related to the canonical momentum of the time t. You can use the Hamiltonian-Jacobi equation to show the volume, the partial derivative of volume with respect to t is just given by the canonical momentum of t. So here I just regard t as a canonical coordinate. T is not the time. T is just because t is just you can think it's just the physical field, and S is the time. So in this aligner, I can find the complexity growth rate is given by the canonical momentum, because the whole action does not depend on t explicitly. The momentum will be conserved, so I can compute this momentum at s equal to 0. That means I can compute this moment at the point A rather than at the boundary. Okay, now there's a very lengthy mathematical computation. I will not talk about detail here. And you can write down the induced metric and write down the volume functional in this way. Okay, you can compute all the mathematical computation, and after some computation, you can find the final mathematical expression for the momentum. It is this mathematical expression. And the basic, if you compute this guy at infinity, it is very hard to compute it. But I can compute it at s equal to 0. Because I choose the two boundary slices symmetrically. You can think in this picture, I choose SL and SR symmetrically. So you will find, at this point, I define S equal to 0 because it is symmetrically. You will find minus S and the positive S should have the same T. Minus S and the positive S, I'm sorry, minus S and the positive S should have the same Z, but the T has the different sign because this guy is T is positive, but if you use the coordinate time T, you will find at this side, T is a negative value. So you will find, in general, you will need this expression. So if you compute some quantity at T equal to 0, you will find some very simple expression. And finally, I find if I compute the momentum P at the point A, I can find the final expression is this result. And this is nothing but the size of cross section A. So by compare with this definition, here this is a general coordinates gauge, and I find the size has this mathematical expression. And when I compute commensurate growth rate, use the same coordinate gauge, and finally I find the commensurate growth rate is given by this result. So it is just the size of the cross section. So now I have conclusion. The commensurate growth rate is given by the size of cross section A, and if this inequality is true, and then this inequality must be true. So they are equivalent, they're the same thing. If I can prove this inequality in general case, then in fact I have proved the Lloyd bound in complexity volume conjecture.
Run-qiu?
Okay.
Just one check. So when you did in this slide is very standard computation of the complexity volume conjecture, right?
Yes.
And at the end of the day, you found the equation in the bottom, in the center.
Right.
And then you found a new interpretation of this equation. That's the logical step, right?
Right. So I can just, I firstly choose a coordinate gauge and compute complexity growth rate. And finally, I find the growth rate is given by the size of cross section just at the middle point. That means if you want to compute complexity growth rate, you only need to compute the size of cross section A.
Right. So I mean, up to this point, it's a standard volume conjecture computation.
Right. Yeah.
Right. And only this part you found a new interpretation of this equation. That's that's the whole structure, right?
Right.
I see. So then in this structure, you first explained what this guy means in your own language. And the last part, you showed that this is really nothing but C dot.
Yes.
Okay, I got it.
But in fact, my logic, I first do not find it has relationship to complexity. So I just because when I just find for Schwarzschild black hole, the cross section has an inequality. So I want to start this inequality. But after then, I find it has some relationship to complexity.
Okay, I see. Okay, thank you.
This is why in my PowerPoint logic, I first introduce the size of cross section and then talk about complexity.
Okay.
Because complexity is not my original purpose, but finally I find it is a very good result.
Okay, I understand. Yes, thank you.
Okay. So at current, okay.
Yes. So in the plot of this complexity as C dot as a as a function of time. Originally it's 0, but it grows and then it goes to constant, right?
Right.
So in this, so this behavior actually can be easily kind of understood from this geometry. Is it
In fact, if you think about the Schwarzschild black hole, yes, you can find light, because if you increase the time, that means you rose up SR and SL, right? Yeah, so A, of course, will be rose here, A. So at beginning, A at this point is at the horizon. Then you will find, because F is 0, if you think about the Schwarzschild black hole, A, V also 0, so this guy is 0. So you mean kinetic growth rate will be 0 at starting point.
So what was F1V? I'm sorry.
V stands for the angular momentum.
V is the angular.
Yeah. So if you think about Schwarzschild black hole, so this metric component is 0. So only function F appear.
And what was F?
F is just if you straight down the usually Schwarzschild black hole, you have the minus FDT square.
So it is 0.
So it's in this coordinate. You can think this coordinate. So if you think Schwarzschild black hole, this guy is 0 and F chi equals to the 1 over F. So F is just the function here.
I see. So it's 0 on the horizon.
So at the starting point, you will find the kinetic growth rate is 0 because this is 0. And when you rose SL and SR, A also will be rose and A is non-zero. Anyway, you will find this point has a maximal value. So it will grow and then will approach to a maximum value.
I see.
But for very general black hole, I don't know how to understand this point easily.
Okay.
Maybe it have different behavior. Okay.
I see. So it's like some the difference of the change of the volume itself as time goes. So that's the cross.
Right. Yes.
Nice. Okay.
So here, all this is the result based on assumption the space-time is stationary. If the space-time is not stationary, of course, you can also compute the maximum volume. You can also compute the volume growth rate, but the momentum is not conserved. So I cannot use the momentum at point A to send momentum at the boundary. In this sense, the cross-section will not give us the volume growth rate.
So even though you don't use any Einstein equation, in fact, I'm surprised that the all of the result actually depends only on the point S equal to 0. Since volume
right.
all over.
Yeah, yes, currently I do not use the Einstein equation because this is simply geometrical relation. The volume is defined by geometry and all these outguy are computed by geometry. I don't know, but if you want to prove this bound, the Einstein equation must be used.
Of course, yes. But as for this formula, I think it's interesting that only the information at S equal to 0 governs the whole structure.
Right.
So is it because of the conserved quantity P?
Yes, this is the essential reason.
Nice. Thank you.
Okay.
Can I check one point?
Okay. Yes.
It's Dongsu, or you assumed somehow exist, as you mentioned, existence of Killing symmetries.
Killing symmetry?
Or Killing vector.
Yeah, because I require the space-time is stationary. That means it must have a Killing vector. Its Killing vector is time lag at the boundary.
So can you say if we don't have a killing symmetry, I mean the black hole is not stationary, then what happens with this bound?
If the black hole is not stationary, then this bound may not be true. In fact, I noticed there's yes. In fact, I find there was a paper last year to consider the dynamic black hole and find even in volume conjecture, the commensurate growth rate may have maybe larger than the mass. It means the knot bound is not true in dynamic black hole. I remember there's a paper to talk about that.
I see. So in general, without this killing symmetries, we don't have this bound generically. Is that the one you claim, right?
Yes.
Oh, okay. Thanks.
Okay. Okay, I will go on. Okay, let's just give exact statement about my bond. Here, I will not talk about the details of the proof, but if somebody have some interesting about the proof, you can just read the paper here, this paper. Here, just give a very exact statement of this bond. So I obtain a conclusion for stationary black hole if it satisfies 3 requirements. The outermost horizon is a connected Keeling horizon and has a positive surface gravity. This means the temperature is positive. And the space-time is asymptotically spherical or planar Schwarzschild ADS black hole. And the dominant energy condition and Einstein equation are satisfied. Then we can always obtain this inequality. Here, I just missed the ADS radius, but if you, in general, you can add ADS radius here. And as a corollary, you can find the commensurate growth rate in volume conjecture will satisfy the Lloyd bound. So let's make an explanation about here, asymptotically spherical or planar. This means the space-time can not have spherical or planar symmetry, but at the boundary has spherical or planar symmetry. So here I just require a asymptotically spherical or planar symmetry. And in fact, currently I can only say this is a conjecture because I only can prove it in some situations. So in my paper, I prove it for spherical or planar symmetric case in arbitrary dimension. Or if we focus on 4-dimensional case, I can show in general case without spherical or planar symmetry. But in higher dimensional case without spherical or planar symmetry, I do not find the proof currently. So this inequality, I think it is still a conjecture in general case. So if somebody care about the details of proof, and I just suggest to read this paper because it is a little mathematical and not easy to explain in a short talk. Okay, let's make a field discussion. In fact, currently, I just gave an upper bound by the mass of black hole. But in some situation, maybe we have a more tighter bound. For example, if we think the black hole, it has 2 horizons. So there is a next outermost horizon. So we think about the cross-section between these 2 horizons. And if you think about the 0 temperature limit, this means 2 horizons will be close to each other. And you will find, for example, in iron black hole, you will find if the 2 horizons touch each other, then the size of cross-section will be 0. But currently, the mass of the black hole can be arbitrarily large. This means in low temperature limit, there may be a tight bound. It's given by the temperature rather than by the mass. Because mass cross-section in this case is 0, mass can be arbitrarily large. Temperature is 0. So you may guess in low temperature limit, we have an upper bound controlled by temperature. For example, for BTZ black hole, direct computation shows the bond can also have this form. So it's just proportional to the temperature. So in this sense, maybe we have a tight bond in low temperature limit. Currently, I do not find a universal expression for this bond except for the BTZ black hole. So I think this is an interesting question in the future. And in fact, I find this bond has a generalization in asymptotic flat spacetime. In flat spacetime, this bond has a different mathematical formula, but basically it also controlled by the mass of black hole, but not direct proportional to the mass. It is some power of the mass. And in black hole, if you think the black hole is formed by collapse, and you will find if this is a very large black hole after the collapse, then the black hole will have some Hawking radiation and so on. And because if you think about a large black hole, so the Hawking radiation is very small, and you can just think this black hole is a stationary black hole. And in this case, I can find the maximal volume inside black hole satisfy this inequality. So the volume will grow, but the growth rate is bounded by the mass square if we focus on the 4-dimensional black hole. So this is the generalization in asymptotic flat spacetime. And now we can use this inequality to estimate the largest volume once appear inside the asymptotic black hole, asymptotic flat black hole, because we know the black hole will evaporate, and the evaporating time will proportional to the qubit of the mass. So that means at this time scale, we can regard the black hole as a stationary black hole. And then for stationary black hole, we find the volume growth rate will proportional to m squared. Then we can find the maximal volume once appear in the evaporate black hole will proportional to the mass to the power of index here is 5. So by this in this equation, we can just obtain the largest volume once appear in the black hole. And in fact, this guy, because the index here is 5, so you will find this volume is very big. For example, if you think about the black hole has the mass of our sun, so if you use the area radius to measure the how big of this black hole, you will find this black hole is very small. It's only 3 kilometers. However, if you think compute its volume, the volume is very, very huge. And if you use the volume radius to stand for this black hole, you will find the volume radius is in this guy. So there's many the difference, many orders. So that means if the black hole has a very small area but has a very, very big volume. So what does it mean in physics? I don't have any good answer currently. So I think this is also an interesting question based on my result. Okay, let me make a short summary. So in this talk, I talk about a universal inequality about the geometry inside black hole. And I find an upper bound for the size of cross section. And this upper bound has very important application to holographic complexity. And agree with the argument of quantum information because it is just equivalent to the Lloyd bound in complexity growth rate. So I also make a first step towards the holographic proof on the Lloyd bound. Because if you think the CV conjecture is correct, and if you can prove the bound about the cross section, in fact, you then give a holographic proof about the Lloyd bound. So I think this is make a first step towards the holographic proof on the Loroyd bond. And it also give us a conclusion that the vacuum black hole is the fastest computer in the nature, because Kamles's growth rate stands for the computation speed in some sense. So I also give an estimation on the largest interior volume of a large evaporating black hole in a asymptotic flat spacetime. Okay, I will stop here. This is my talk, and thank you.
Okay, thank you, Run-qiu, for your very interesting talk. So, is there any question or comments for Run-qiu?
Can I ask a question?
Yeah, sure.
Okay.
In your inequality on the right hand side, we have mass times ADS radius.
Yeah, I just returned the beginning. Yeah, this guy. So the mass times ADS radius.
So if we apply in general this formula to generic black holes, then where mass I can understand, where mass is generically defined. LADS scale is given by what?
This important.
Consider flat space Schwarzschild black hole.
Here, this equality only used for asymptotic and ADS spacetime. So.
Oh yeah. That I understand the word.
Right, and if you think about asymptotic flat spacetime, I have a different result here. So, but if not, for more general, I don't know the result. So this is the case for asymptotically flat spacetime. Here is also the mass, but here you should compute the mass density rather than the mass. After you compute the mass density, and then they have some power. So it's not just proportional to the mass. So in asymptotic flat spacetime, it is a little collected than asymptotically ADS.
Oh, I see. So the formula is only for the asymptotically flat, asymptotically ADS spacetime. Okay.
Yeah,
okay.
In fact, we have to prepare some requirements on the asymptotic behavior. If you do not make any assumption, then I think there's no any universal result.
I see.
Okay, any more questions?
Hello, Run-qiu. I have a short question.
Oh, hi.
So do you have any comments on the d equals 1 case, or even d equals 2 in this flat case?
In d equals 2, this is two-dimensional. In asymptotic flat case, we cannot obtain the three-dimensional black hole, right?
Okay.
Yeah, for example, BTC black hole is asymptotic ADS. So I don't know if we can obtain asymptotic flat three-dimensional black hole. Anyway, so this formula cannot be used into the d equals to 2. That's in asymptotic flat case. But in ADS case, we can use the three-dimensional black hole. D equals to 2, that's BTC black hole. But for two-dimensional black hole, for example, the JT gravity, and we think about the two-dimensional black hole. So I think this formula is not true, because I used the Einstein equation. So the action should be the action of the gravity side should be the Hilbert-Einstein action. So in two-dimensional case, I mean the two-dimensional space-time, it is trivial. But in JT gravity, it's Danilton coupled to the curvature, so it is not the Einstein equation. So
see,
this
I see.
conclusion is not true.
I see. Thank you. Yeah, another short question in your last slide, you show the very huge volume. So I
Right.
missed so what's the connection between this volume and your, is that complexity or your cross section?
No. I just, because I consider the asymptotically flat case. So I don't know if in flat case we can obtain a holographic explanation or not. So here there's no relationship to the complexity. I just want to know, because once the black hole appear, it will evaporate, and finally the black hole will disappear. So then I want to understand what is the maximum volume in this black hole, because the volume, once black hole disappears, the volume becomes zero. So in this sense, there must be a maximum volume once appeared in this black hole. So I try to compute the possible maximum volume. So then I find even the horizon area radius is very small, but the volume inside may be very, very big.
I see, yes. Thank you very much.
Okay, so any more question? Okay, then let's finish this session officially. Then probably we can discuss